Right, time to talk about how to do these sample reactions and the steps you would take in order to solve them completely. We definitely want to be sure that we pay attention to the directions. So, in other words, do what they say. Make sure your answer's inside the box. You don't have to specify solid or aqueous unless directed to, though we will in these examples just to make clear why we make some of the decisions that we do, at least where appropriate. The yes or a no is fine. That's what we'll do for yes, it will occur, no, it won't. And yes, in this class for oxidation reduction, we do focus on cases where one thing gets oxidized, one thing gets reduced, and it's only one of the elements rather than an entire compound. All right, so that said, let's look at this. So here's a reaction. Will it occur? What element gets oxidized, what gets reduced, whatever. We actually, for this particular kind, we recognize this is single displacement because you have an element reacting with a compound, and it's not O2, it's another pure element, so it's element plus compound, and it isn't O2. That tells you single displacement, which means you go look at this right here, and this tells you, before you even do the reaction, you already know whether it's going to occur. So in a single displacement reaction, like replaces like, so the pure element switches places with the thing that is like it, and chlorine, which makes an anion when it ionizes, will replace not the manganese because that's a cation, but iodine, the other anion. So chlorine and iodine will switch places with each other. In fact, maybe I'll even write that out here to make clear what I'm talking about. Chlorine plus manganese iodide. The chlorine and the manganese will switch places so that, the chlorine and the iodine will switch places so that it's now iodine is the pure element by itself because the iodine goes here, and the chlorine is now attached to the manganese. Now, why did I write I2? Because Hofbrinkel, that's the word used to remember the diatomic elements. Iodine is a diatomic element. Now, that's a digression. Again, I said, will it occur? You use the activity series. So I wanted to do this to make it clear that chlorine and iodine will switch places with each other, so those are the ones you have to look at because they're the ones that are doing this. Now you will find neither chlorine nor iodine here because you have to look here in the case of it being a nonmetal. So remember, the element must be above the one it wants to replace, or rather the pure element needs to be above the one it wants to replace on the list. So we look. You'll notice chlorine is indeed above iodine on the list. What that means is, yes, this reaction can occur. Now, we aren't done here, though. This isn't balanced, and we didn't even check to make sure this is the right formula, because consider manganese is a transition metal. So manganese paired with iodine. Iodine's a 1 minus charge, so manganese is a 1 plus. We need to make sure this is the right formula for here. Because remember, step 1 was we switched the parts, step 2 was fix the formulas. So putting the iodine out here, I put it as a 2 to fix that and make it correct. For manganese chloride, we assume manganese retains the same charge of +1. Chloride, we look it up on the periodic table and verify that chloride is a -1 charge. And so it turns out in this case that you just leave it as manganese chloride, but sometimes you might have a 2 or a 3 or 4 here, depending on what the charge of this is. But in this particular case, it works out to be like this. Nonetheless, we got to balance. So if there's 2 iodines, we got to put a 2 here. And we're going to make it 2 iodines, so that makes 2 manganese. So we got to put a 2 here, and that works just fine because that also makes 2 chlorine to balance 2 chlorine. So that's good. Now, what got oxidized and what got reduced? I'm going to rewrite the equation up here to help make that a little easier to see. So we got I2 plus MnCl. In order to figure out what's oxidized and reduced, you got to figure out the oxidation number. Pure elements are neutral. Manganese is not a pure element, so we're going to ignore it. And then chlorine and iodine are the only 2 then. All right, so iodine is a -1 charge when it's in a formula, and the same is true for chlorine. It's also a -1 charge. So what happened is chlorine went from a 0 to a -1. And if it was from 0 to -1, it must be gaining an electron, and gaining of electron is this reduction. Iodine went from -1 to 0, so it's losing its negative charge, it's losing its electrons, which means it's oxidized. So that's iodine. All right, and that's how you answer the first one. Next, This is a decomposition reaction. This delta means heat added. You are going to get it splitting into pure manganese and pure chlorine. Now that said, let's do that properly down here. Manganese with 4 chlorines splits into manganese and pure chlorine. Now remember, that's not the formula of chlorine, this is. So a simple thing with just 2 elements, this is decomposition. It will split into the elements it's made out of when it's just a simple, what we call binary compound of just 2 elements together. So we just got to balance it. That's 4 chlorines. Okay, let's make that 4 chlorines and 1 manganese, 1 manganese. Okay, that's it. All right, so we just make sure to answer the questions. If it doesn't ask whether it's oxidized or not, then you don't have to keep track. If it doesn't ask whether it occurs, then you don't have to keep track of it, okay? We just answer what's there, and we don't bother answering a question that doesn't exist. All right, now, here, a double displacement reaction. I know that because it's one compound reacting with another compound. Will it occur? You don't know that until you figure out what the products are. So let's predict the reaction. Lithium carbonate reacts with iron, which is paired with 2 sulfates. And that is going to produce, the iron will switch over to being on the carbonate. And then the lithium, let's switch that over to the sulfate. So that was step 1 that we do. We switch the parts. Step 2, we got to fix the formulas. So iron, we don't know what charge iron is because it's a transition metal. So we got to figure out the charge in order to figure out what formula this is. So FeSO4 2. SO4 is a -2 charge. There are 2 of them. So 2 times 2 is -4 total charge, which means the iron must balance by being a +4. Therefore, the charge of iron is +4. So Fe retains its +4 charge in the product side, and then it gets paired with carbonate, which is a -2. So this is going to produce something that has 2 irons and 4 carbonates. So Fe2CO3 4. But that's a 2 to 4 ratio. A 2 to 4 ratio is the same as a 1 to 2 ratio. So we simplify that from 2 to 4 to 1 to 2, as in 1 iron and 2 carbonates, like this. So I'm going to adjust the formula to be 1 iron and 2 carbonates. Here, this is a little simpler because lithium is always a +1, and sulfate is always a -2. So we can just go straight to predicting the formula. It's going to have 1 sulfate and 2 lithiums, which is to say that. So once that's done, let's take a look. We got 2 lithiums, 2 lithiums, 1 carbonate, 2 carbonates. Oh, we got to times that by 2. All right, fair enough. Oh wait, well that times our lithiums by 2. We got to times this by 2. Okay, well now we got 2 sulfates. Oh look, good, 2 sulfates. And then we got 2 carbonates. And oh look, good, 2 carbonates. All right, so actually that works out nicely. There's the balanced reaction. Now, will it occur? Although the instructions say you don't need to specify whether it's solid, liquid, aqueous, whatever up here, you're going to have to do that in order to figure out whether or not it occurs. Now, 2 have already been done for you. Look. They're both aqueous. Now, why do we have to find this out in order to find out whether it occurs? Because, as a reminder, we say a double displacement reaction occurs if anything anywhere is not aqueous. The only way it doesn't occur is if all 4 things are aqueous. So let's take a look. Is iron carbonate aqueous or not? So we look not here, but here. And we look at the anion. The anion will always tell you on this chart whether it dissolves in water or not. So carbonate is right here. It says insoluble. That means will not dissolve, which means we would write solid. So carbonates are generally solid. And here's the exceptions. If iron was listed in the exceptions, it's not. But if it was, then we would say, nope, not solid, it's aqueous. But since iron's not an exception, that means it's solid and it stays that way. So we put solid because it does not dissolve in water. Here, by the way, we already know, yes, the answer occurs, but let's just be thorough and look here too. Lithium sulfate. Sulfate is right here. Sulfates are soluble unless paired with one of these. Notice lithium is not on this list. Therefore, it is soluble, which means we put an AQ. Not that that matters, though. The fact that something was not aqueous means, yes, this reaction occurs. Again, the only way to get an answer of no is if everything everywhere is aqueous. If anything anywhere is not aqueous, yes, it's a reaction. All right, let's continue. Okay, solid barium and aqueous aluminum bromate. An element plus a compound, and the pure element is not oxygen, so it's a non-oxygen element plus a compound. This makes a single displacement reaction, which means we can expect an element plus a compound, as in we can expect barium to switch places with the element that's like it. Barium's a cation, aluminum's a cation, so barium and aluminum will switch places. So barium plus aluminum bromate. If barium and aluminum switch places, you're going to get aluminum as the pure element, and then barium will bind with the bromate. That's not the correct formula yet. I've just switched the pieces. I need to fix the formulas, but first, before we do that, that just, in order to answer will occur, you can look at this and know that this is going to happen, and even before you solve this, you can already figure out whether it's going to occur or not, because since barium and aluminum is going to switch places, the pure element, barium, needs to be above aluminum on this list here in order to successfully replace it. Is barium above aluminum? There's barium. And down below it is aluminum. Since the pure element is above the one it wants to replace, the answer is yes, this will occur. Now, let me get back to where I was. I switched the pieces. Now I got to fix the formulas. Barium, and already here, is a 2+. Bromate is a 1-. So that means you're going to have 1 barium and 2 bromates in the formula. Okay, we got 3 bromates here, 2 bromates here. Let's use that trick of switching the subscripts. Put this 2 over here and put this 3 over here, giving us 6 bromates and 6 bromates. So the bromates balance. However, we now have 2 aluminum, so let's put a 2 right here. And we have 3 bariums, so let's put a 3 right here. Now it's balanced. Okay, now what gets oxidized? What gets reduced? That's the last piece. So to make that easier, I'm going to write it out up here too. We got aluminum and barium bromate. Remember, the charge of a pure element is 0, so 0 and 0. Bromate is not a pure element, and it's never by itself, so we're going to ignore it. So let's just look at barium and aluminum, because they're the only pure elements. Aluminum is not a pure element here, which means it takes a charge. And you look up on the periodic table, and you can prove to yourself aluminum is a +3. Barium, you can prove to yourself it's a +2. Sorry, I pointed to the wrong thing, right there. So, barium goes from a 0 to a +2. That means it's losing electrons. Loss of electrons is oxidation. Aluminum goes from +3 to 0. That means it must be adding negative charge in order to cover up the positive, which means if it's adding electrons, it's getting reduced. All right, so that's how you do that one. Moving on. Sodium plus sulfur. What gets oxidized? What gets reduced? Well, first of all, you have element plus element, so you're going to have some version of sodium and sulfur here. We can predict exactly which by doing some crossing of the charges. Sodium is a plus, sulfur is a -2. You can prove that to yourself by finding sodium amongst the pluses and sulfur amongst all the -2s. Switch the charges, you're going to get 2 sodiums and 1 sulfur. So Na2S. But let's do that here properly. Na plus S8 makes Na2S. We can even balance that reaction. 8 sulfurs, yes, that's right, 8. That's 1 sulfur, so let's put an 8 here. 8 times 2 is 16, so 16 sodiums. All right, there we go. Now, Which element gets oxidized, which one gets reduced? Pure element has a charge of 0. Pure element has a charge of 0. When it's in a compound, sodium's got a charge of +1, sulfur's got a charge of -2. So sodium went from 0 to a +1, which means it lost negative charge. That's the only way it becomes positive, which means it lost an electron, and losing an electron is called oxidization. Therefore, sulfur is the other one. But how do we know that? Because sulfur gained negative charge, which means it gained electrons. That's how you know it's reduction. All right. So, well, that's that one. Next, combustion of dodecane. Combustion. We have to understand combustion means reacting with oxygen. So it's plus O2 whenever you see combustion. That means C12H26 plus O2 makes, remember, combustion of anything with carbon makes carbon dioxide. Combustion of anything with hydrogen makes water. Fair enough? Let's start balancing. So 12 carbon, let's put a 12 right here to make 12 carbon. All right, that's good. In fact, let me do a little something. Well, okay, yeah. So 12 carbon, and then 26 hydrogen. So I'm going to put a 13 here. That way I can see 26 hydrogen here also. Cool. Carbon good, 12 and 12. Hydrogen good, 26 and 26. Now oxygen. Okay, 12 times 2, that's 24 oxygen. Plus, how many are here? 13 times 1, that's 13. That's 37 oxygen. So we got to get 37 oxygen here. But remember, this is not O, this is O2. So how many O2s give you 37? I don't know. Here's how you find out. You need 37, so put a 37 there. Make it into a fraction, and on the bottom, put the number there are. So you need 37 oxygens, and each molecule has 2, so 37 halves. If you were to actually do 37 divided by 2, that comes out to, let's see, 36 would be 18, so 18.5. So if you put 18.5 there, it's the same thing. But you can't have 37 halves or 18.5 in your final answer. So what do? See that bottom on the fraction where it says a 2? Multiply by whatever number's on the bottom. Alternatively, just times the whole equation by 2 and hope it gives you whole numbers for everything. If it doesn't, try multiplying everything by 3. If that doesn't work, try multiplying everything by 4, and keep going until everything's a whole number everywhere. But the trick is, the bottom of this fraction right here, that's the number you times the whole equation by. That's a 2, so I'm going to times the entire equation by 2. So this times 2 makes a 2. This times 2 makes just 37. So I'm going to white that out and make that bigger and easier to see. So plus 37 O2s. 12 times 2 becomes 24. So that's now 24 CO2s. And then 13 times 2 becomes, let's get that out of there, we go, 26 H2Os. 24 carbon, 24 carbon. 2 times 26 is 52 hydrogen. 2 times 26 is 52 hydrogen. 37 times 2 is 74 oxygens. And it turns out 24 times 2 is 48 plus 26. Do that on a calculator, it does equal 74 oxygens. So we've got the correct number of things equal on both sides. That's our final answer. All right, now, onward then. Magnesium plus copper 2 nitrate. Okay, it's given to you in words. You got to turn it into an equation. So magnesium, whenever you see just the element, especially if it's a metal, you just write Mg. Because it's a metal, the pure metal has that formula. Copper 2 nitrate, that's copper with a +2 charge. And nitrate is NO3 with a 1- charge. So we switch the charges. So 1 copper and 2 nitrates will be in the formula. Cu NO3 2. So this is copper 2 nitrate. So let's do it. Magnesium plus CuNO3 2 makes what? All right, so we see magnesium will switch places not with nitrate. Nitrate's negative and magnesium is positive, but it will switch places with copper because magnesium is positive and copper is positive. That means copper comes over here to become the pure element, and magnesium joins up with the nitrate. Now magnesium, okay, that was a switch in the parts, yeah, but magnesium is a 2+, nitrate is a 1 minus. So when you switch the charges, you're going to have one magnesium and 2 nitrates. So let's make that 1 magnesium and 2 nitrates. Cool, so now we just go balance. 1 magnesium, 1 copper, 2 nitrates, 2 nitrates. We're done. It's already balanced as written. So that's how you do that one. All right, let's set that aside. Let's do another one. Lead 2 acetate and iron 3 chloride. So lead 2 acetate. All right, let's see. Lead is Pb with a 2 plus charge because it's lead 2. And then acetate is C2H3O2 with a minus charge. So lead 2 acetate is going to involve 1 lead and 2 acetates in the formula. So that's Pb C2H3O2, parentheses, 2 of them. And then reacting with iron 3 chloride. Okay, that's iron with a +3 charge and chlorine with a minus charge. So let's switch those charges to make 1 iron and 3 chlorines, or shall I say FeCl3. And now the thing is, will it occur? So this is double displacement because you have 2 compounds reacting. If you want to know whether or not it's going to occur, you're going to have to look not here, this is for single displacement reactions, not here, this is also for single displacement reactions, but here. We're going to have to figure out for everything whether it's soluble or aqueous, and if it's soluble or not, because if everything's aqueous, no reaction. If something is not aqueous, then yes, we say there is a reaction. So that means we got to predict the products first before we can actually decide whether or not the reaction occurs. So the lead and the iron will switch places. So the iron will pair up with the acetate and the lead will pair up with the chlorine. So the iron goes with the acetate C2H3O2 and then the lead will go with the chlorine. So I switch the parts. Now I got to fix the formulas. We know iron's a +3, so it's going to stay that way. Fe3 plus C2H3O2 minus, switch the charges, 1 iron, 3 acetates. There it is. Lead chloride, Pb, it says it's a +2, so we assume it stays the same. And then chlorine's a -1. So we switch parts, or switch the charges. We have 1 lead, 2 chlorines. That's the formula. We then balance. 1 lead, 2 acetate, 3 acetate. Oh, we got to switch we got to make that work. Okay, so let's put this 3 over here. Put this 2 over here. That way it's 3 times 2 is 6 acetates, and also 3 times 2 is 6 acetates. Now, that also means 3 leads. So I got to put that 3 right there. But it also makes 6 chlorines. So if I put a 2 here, that makes 6 chlorines. That also gives us the 2 irons that we need. So there we go, that's the balancing. Okay, now, having done that, we got to look these up and figure out which ones are aqueous or solid or what. Because if it isn't aqueous, we assume it's solid. So we look them up by the anions. So let's do the acetates. So look at both the acetates first. The acetates are right here. And it says acetates are soluble. That means they're all aqueous, with no exceptions. So all the acetates are aqueous. So that means we're going to put AQ by this acetate and AQ by this acetate. Not because we're required to, but because we're doing this to keep track so that we can figure out what to put for up here. Now, the chlorides, where do we find those? Right here under halides. So anything paired with a chloride is a halide. Halides are soluble, so they're always aqueous unless paired with one of these. So iron chloride is not one of the exceptions, so it's soluble, it's an aqueous. But lead chloride, notice lead is an exception. So, oops, I pointed the wrong thing. Although chlorides are soluble, because lead's an exception, that means it's not soluble, and if it's not soluble, we're going to put solid. And because of that, we have something that's not aqueous, and because something is non-aqueous, yes, the reaction occurs. And that's how you do that one. Finally, these. This is just to check that people know how to do what we did here, which is read stuff off that chart to see if it's soluble or not. So you're going to, if it will dissolve in water, if it's soluble, you're going to put yes for dissolves. If it's not soluble, you're going to put N for does not dissolve. So will copper 2 chlorate dissolve? We find chlorate on here. Chlorate always dissolves with no exceptions, so we say yes. All chlorates dissolve. Will strontium hydroxide dissolve? Hydroxides, it says, are insoluble, therefore they do not dissolve. However, notice strontium is an exception. So strontium's hydroxide, unlike the usual rule, will dissolve. So that's a yes. Aluminum chromate. Aluminum chromate. Let's find chromate. We find chromate right here. Chromates will not dissolve. Notice that aluminum is not one of the exceptions on that list. Therefore, chromates don't dissolve, and this is not an exception, so we say no, it won't dissolve. Next, lead-3 bromide. So we look at the anion bromide. There it is. It's a halide. Notice there's lead right there. What's this all about? Well, bromides dissolve unless it's with things such as lead. Therefore, no, it will not dissolve. Barium sulfate. Sulfate is right here. Oops, there we go. It was out of view for you, the viewer. And they dissolve unless paired with things such as barium. So, for that reason, we're going to say no, it will not dissolve, because although these usually dissolve, barium is an exception. Next, carbonate. Carbonates do not generally dissolve in water. However, there are certain exceptions. Ammonium is one of those exceptions. So although carbonates don't usually dissolve, this one does, because ammonium is an exception. Finally, phosphate, magnesium phosphate. Here's phosphate. Phosphates do not dissolve unless paired with one of these. Again, we're talking magnesium phosphate. So phosphates don't dissolve. Magnesium is not one of the exceptions. Therefore, we stick with the default of do not dissolve. And so, since they don't dissolve, we put an N for no. Well, all right, ladies and gentlemen, there it is. That's all the answers. Happy study.